Good morning, sir.
Hi, Rahul. Good morning. So I think Samantha won't be joining us today. So you guys remember what we learned in the last class, or you forgotten?
We were learning regression models. That much I remember.
Correct. So it's been a long gap, no? Like about a month gap. Are you able to see the screen?
Yes, sir.
Yes.
Let's do one thing. Let's have a quick recap. Okay. So basically, we discussed about machine learning and its classifications, correct? Basically, machine learning is classified into supervised and unsupervised approaches, correct?
Yes.
Under supervised, we have
Regression and classification.
regression and classification. Whereas under unsupervised approach, we have
Clustering and dimensionality reduction.
Okay, correct. And in this whole regression, in this whole machine learning, we focused our topic on regression, and we started studying the first regression model, that is linear regression. Okay. Under linear regression, we talked about the line equation, which is given by y equal to x beta, which can be further elaborated into beta 0 plus beta 1x and so on. Correct. Now, what are these betas?
They are constants.
They are coefficients. These are coefficients. What is x?
Variable.
It's an independent variable. Correct. And what is y?
A dependent variable.
It's dependent variable or target variable. Correct. And we discussed about having optimizing the equation, optimizing this equation to get a best fit curve by minimizing the error. Correct. So error is given by actual minus predicted, whereas the prediction is through this equation, through this model. Okay. Now, how do we optimize it? By minimizing the error. Error is given by, how did we validate the model with respect to error? One is your RMSE, correct? And the other one is your R square.
R square.
Okay. What is RMSE?
Root mean square error.
Correct. You take your error, that is actual minus predicted. You take the square of it, correct? You take the mean of it. So summation, and you take a mean of it, and you take a square root of it, correct? Now this RMSE, should it be more or less?
It should be minimum.
It should be as low as possible. And the range could be from 0 to infinity, correct? This number will be always positive in nature. It can go to from 0 to infinity. Lower the better. Coming to R square. How did you define R square? R square talks about the, if this is your regression equation, your explained and unexplained variance, correct? This is your explained variance. This is your unexplained variance. So R square is given by your total variance, that is nothing but your explained variance or total variance
minus
unexplained variance divided by
total
total variance. Okay, what is the range of this? That will be in between 0 and 1, correct? Should it be more or less?
as high as possible.
This should be as high as possible. Okay, after this, after clearing all this, we learnt about assumptions. I think in the last class we discussed about the first assumption, that is your target variable should be normally distributed, correct? You guys remember this?
Yes, sir.
Okay, basically in any of the data frames you have and a y, correct? These are explanatory variables or independent variables. This is your target variable or dependent variable. So the distribution of this should be normal. Okay, now how do you check this? What is the check?
By plotting.
One is by plotting, that is your KDE, correct? What is the second check?
Description.
Dot describe.
Dot.
That is mean equal to median, correct? Or you check the skew, how the skew is. Now let's say your target variable is not normally distributed. Okay, let's say your target variable is not normally distributed. How do you correct it?
By standardizing.
By standardizing, that is you take
the variable minus mean by standard deviation.
You take log. Oh, sorry. You take log of target variable, or the other part is you take the square root of target variable. Are you with me?
Yes, sir.
So now, before we move on to the second assumption, okay, let us focus a bit more on your first assumption. We spoke about a very common example in linear regression, that is your temperature versus ice cream scales. Correct? And we had a linear regression curve, something like this. Let's say these are all the temperature points. Okay. Now, basically, why do we need assumptions? Why do we need assumptions? Why do you think we need assumptions?
So that the data is simplified and we can solve.
In a simple word, like for the mathematics to work in the background, for the math to run in background. Okay. Now, in this discussion, we concluded that your ice cream sales is given by beta 0 plus beta 1 into temperature, correct? Now this is our model for future prediction, correct? Now let's say that the temperature equal to 32 degree, okay, and we have the prediction of ice cream sales equal to 50. Okay. We have the prediction as 50. Now, are we 100% sure that we will sell 50 ice creams?
No, it's approximate.
It is just approximate. So I can say that we are not looking for 100% accurate model, but we are looking for a good enough model. Okay. Now, is it possible that most of the discussion remain on the temperature, but somehow there are few people, okay, who just feel like eating ice cream? There's just few people who like eating ice cream that day. We have benchmarked the whole discussion on ice cream sales on one variable, temperature, but there are few people who just feel like eating ice cream that day. Okay, or some people who do not want to eat ice cream. So that 50, the prediction of 50 is not exactly 50, right? It can go above or it can go below.
Either ways.
Okay, there will be some variance. So how can we represent this variance? How can we represent? So basically, my ice cream sales will be beta naught, beta 1 into temperature plus I give this variance as the error. Correct? Now, this is my calculated. Correct? Whereas this just represents that instantaneous feeling of whether I should eat ice cream or not. Are you guys with me?
Yes, sir.
Yes.
Hence, this particular equation or this block of the equation gives me real values. Correct? It translates real values and this becomes your variable. So now this is just a representation. Okay, the real reason why I bought is for machine learning or for linear regression. The error is assumed to be normally distributed. Okay. Okay. So now the prediction for tomorrow is 50 ice creams. How many more or how many less? It could be I may sell 5 or 4 ice creams more, or I may sell 3 or 5 ice creams less. We don't know. It all depends on this extra feeling like people wanting to have ice cream or not. So this extra feeling, this doesn't depend on the temperature, correct? So this error depends on the extra feeling or the mood of the people. So this prediction or this mood is probabilistic, correct? You guys agree with me?
Yes, sir.
So since this is probabilistic, that is why we consider this as normally distributed. So in this equation, the temperature is normally known to us. Beta 0 and beta 1 are calculated, correct? So if error is normally distributed, that means ice cream sales is also normally distributed, correct? You guys agree with me? So the up and down movement of my target variable is only because of this error or the mood of the people. Clear? Are you guys with me?
Yes, sir.
Shaina, is it clear?
Yes, sir.
And hence our argument that when I say that my target variable should be normally distributed, it means that in the background my error should be normally distributed. Okay. That is why, since in linear regression we do not directly have the error in the data, which is basically calculated later on, we have the target variable and we go with the assumption that target variable should be normally distributed. If this is normally distributed, that means your error will be normally distributed. Okay. Is it clear? No. Let us move on to the second assumption. It's clear, right? First assumption is clear, right? Rahul, first assumption is clear, right?
Yes, sir. Yes, sir. Clear.
Okay. Now, coming to the second assumption, it states that there should be linear relationship between a dependent variable and a independent variable. Okay. Now, in my data set, I have my independent variables or explanatory variables and my target variable or the dependent variable. What this assumption says is that if I do a scatter plot with respect to one independent variable and my target variable or a dependent variable, I need to get a linear relationship. Okay, I need to get linear relationship in this distribution. So how do I verify this? Any ideas?
So could you repeat?
So the second assumption says that there should be linear relationship. Okay, you should have linear relationship between your independent variable and target variable. Okay. Now, which is your independent variable? These are your independent variables, correct? And this is your target variable. So the second assumption says that you should have a linear relationship between the two. So if I pick x1 and y, I should get a linear relationship. The relation should be linear. If I pick x2 and y, again I should get linear. If I pick x3 and y, again I should get linear relationship. Okay. Now, is it clear, Rahul?
Yes, sir. Yes, sir. Clear.
Okay. Now, how do I check this?
By plotting
By plotting, yes. Which plot?
scatter plot.
So I should plot individual scatter plot for x1 and y, for x2 and y, for x3 and y, depending upon how many explanatory variables I have in the data set, correct? I need to check individual relationships. Okay. Now, let's say I take x5 and y. I don't get a linear relationship. I get something like this, something like a curve. Okay. This is not linear. Okay. How do I convert this into a linear form? Basically,
But taking log, sir.
no, if I take log, this will be much more curve. It becomes something like this.
Okay.
Basically, your x and y, I need to transform it to x square and y. Okay. Or x cube and y. So what happens is, let's say I have the number 2 in x. Okay. If I take 2 square, will be 4. 2 cube will be, sorry. 2 cube will be
8.
2 cube will be 8. Let's go the other way. Let's say we have 2, 3, 4 and 5. Okay. Let's say I square the x-axis. This will be 4, 9, 16, 25. Okay. Now, when I plot this, I get this particular curve. Okay. I get this curve. Whereas, when I plot this, your x-axis will get stretched. When you had 2 over here, my 4 will come somewhere over here, whereas your 4 is over here. Okay, your x-axis gets stretched. When it gets stretched, no, even this curve will start getting stretched, and it will start to look like a straight line. Okay, so this is the transformation we are looking at. Okay, this is the transformation we are looking at. If, let's say, if x square y doesn't work, you can try with x cube y or higher dimension. So ultimately, once you do the transformation, your equation for linear regression will look like y equal to beta 0 plus beta 1 into x square. Or if you replace x square with p, you can put it as y equal to beta 0 plus beta 1 into p. Are you guys with me?
Yes, sir.
Now, this is a very clever tip. We are able to convert a non-linear relationship into a linear relationship. Okay, is it clear? Shall I move on? Shall I move on?
Yes, sir.
Okay. Now, coming to the third assumption. Okay. It says that the independent variable should not be correlated. Okay. In simply put, the explanatory variables must not be correlated with each other. Okay. Now, you guys are very familiar with correlation, right? The correlation constant R. So basically what this assumption says that this correlation constant R should be less than 0.8. Okay. How do I check this? In my data set, how do I check this? Any guesses?
To find the R value, sir.
To find the correlation, yes. I use df dot
DF dot correlation.
correlation or a heat map of df dot correlation, correct? Okay. Basically what this assumption says is that it doesn't talk about anything about your target variable. It only talks about your explanatory variables. Basically your x1, x2, x3, correct? And you have y. But this rule doesn't talk anything about y. It only talks about your explanatory variable. Let's say I plot x1 with respect to x2. I plot a scatter plot. They should not be a linear relationship. They should not be this relationship. This is a relationship where I have r equal to 1. Okay. So the correlation should be less than 0.8. So we also have a negative type form of a correlation, which can be given as r equal to -1. So in order to have the clarity, I put r in a mod and I benchmark it to, it should be less than 0.8. Correct? Or correlation as a whole, R will be in between -1 to +1, correct? Now, this is my -1, this is my +1, okay? Whereas this is my 0. This is -0.8 and this is +0.8. So basically your correlation value can be in this region, and it cannot be in this region. Are you guys with me?
Yes, sir.
Shaina, is it clear?
Yes, sir.
Okay. Now, normally when I do df.core, I get something like this. Correct? x1 with x1 will be 1, x2 with x2 will be 1, x3 with x3 will be 1. Correct? Correlation with any variable with itself will be always 1. Okay. Whereas this region is a mirror image of this region. Correct? So this area, the correlation values in this area, when you plot only the explanatory variables, should be less than 0.8. So except the diagonal, everything should be less than 0.8. Okay. Now, what if R is greater than 0.8? Let's say x1 and x2 are correlated. Okay. x1 and x2 are correlated. So that means both are giving me the same equation, right? Both are giving me the same information, right? I'll give an example. Your apartment price is dependent on your built up area and your super built up area. Okay. So basically your built up area is your square feet of the house, whereas the super built up is nothing but your square feet plus some addition of your common areas. Okay. Now you can physically make out that the values will be more or almost similar. If you see, let's say these are x1 and x2. If this is 700, let's say this is 750. This is 800. This is 850. This is 900, 950. Okay. So when I do a correlation, I get this as r equal to 1. Correct? So both my variables are giving me the same information. Correct? You guys agree with me?
Yes, sir.
So the solution is you have to drop one variable. Let's say you have three variables, x1, x2 and x3. You see the correlation. You get 0.9 here and 0.5 here. And here around 0.3. You have to drop this variable and go with only x1, x3 and y. Because both x1 and x2 are giving me the same information and it is 100% correlated. I don't see the point in using both the variables. I can just drop one variable and go with only other variable. Is this clear? Now, this concept where there is multiple correlation between variables, or where the independent variables are correlated, is called as multicollinearity. I can say the violation of this assumption, where you get a independent variables correlated with each other, is called as your multicollinearity. Is it clear?
Yes, sir.
Yes.
Shall I move on?
Yes, sir.
Okay. Now, coming to the fourth assumption. Normally, the assumptions in linear regression, I would say it is 3 plus 2 and not exactly 5, because you need to always verify these. You need to always verify these, okay? And if these are verified, these are automatically satisfied. If these assumptions are satisfied, these first three are satisfied, then these other two are automatically satisfied. Okay, these two are not very important. Okay, but to have the understanding of what these are, let us understand them. Okay, coming to the fourth assumption, here something cannot be checked initially because this assumption is on the error term and not on the variables which we have in hand. So that is the reason why we will not do this check during our linear regression exercise. Okay, now, and one more positive side is when we check the normal distribution of our target variable initially in assumption number 1. So if my target variable is normally distributed, that means my error will be also normally distributed, and hence this assumption will be verified. Okay, what this assumption is trying to say is, this assumption is known as, this phenomenon of this assumption is known as homoscedasticity, that is called constant variance. That means when I plot my error with respect to my predicted terms, I need to have constant variance. Okay, so the variance in error, when I plot error with respect to my predicted term, should be constant. This is called homoscedasticity, or homoscedasticity is also known as constant variance. It's called constant variance. Okay, so but when we do our linear regression, we will not have our error in hand, correct? Error is something which we get it only after doing the prediction. That is, only after doing the prediction we get our error. So that is the reason why we skip this check and we only check for assumption number 1, that is the target variable should be normally distributed, which also proves that the phenomenon of homoscedasticity is also proved. Are you guys with me?
Yes, sir.
Yes, sir.
Okay, coming to the fifth assumption. Now, this assumption is not very important for your linear regression, but this has something to do with the time series. Okay, it says that there should be no correlation between residual error terms. This is called autocorrelation. Okay. Basically, what it says is the target variable should not be correlated with each other. So for now, we will skip this assumption because you will understand this assumption only when you reach time series and not before that. Okay. Now for now, you need to focus on the first three assumptions. Okay. Number one being target variable should be normally distributed. What is the second one? What is the second one?
There should be a linear relationship between
Correct.
independent and target variable.
What is the third one?
Explanatory variable should not be correlated.
Correct. That is absence of correlation. So before you do any linear regression, you need to verify these assumptions. Only then you move forward with your linear regression. I would say we have y equal to x beta. You need to find betas in such that my error equal to minimum. Now for that, first I need to do my assumption check. Correct. I need to check my assumption. Let's do a thing. Let us do a clear recap of our whole, let's say, SOP, the step-by-step procedure. Okay. Basically, what we do first is my problem definition. Correct. This is my step number 1. In step number 2, I import my data sets. I import my data sets. I import my library. Correct. Okay. In the third stage, what will I do here? I carry out my EDA. Correct. Basically, dot describe, dot shape, or dot info plus some plots. I do my calculation. Correct. You guys with me?
Yes.
Okay. And for a regression problem, I also check my assumptions here. Now, how do I know it is a regression problem? How do I know it is a regression problem?
By checking these assumptions.
No. How do I know it's a regression problem? Forget about linear regression. I want to know why. How will I know it's a regression problem?
Whenever we have to estimate a value based on the data which is given.
Okay, that is very generic answer, Rahul. How will I know it's a regression problem? Basic classification of machine learning will be your supervised and unsupervised. What is the difference here? What is the difference between supervised and unsupervised approach? In supervised approach, my target variable is known, whereas in unsupervised approach, I don't have my target variable. Correct? Once again, supervised approach is divided into my regression and classification. How do I know the difference here? My regression, the target variable, the output is continuous in nature. Classification, it's just a classify whether I need to go to office or not go to office. Is this an apple or a banana? It's just classification. You have your output is not continuous. Correct? Are you guys able to recall?
Yes, sir.
Okay. Now, how do I know it's a regression problem?
By looking at the target variable.
Yes, it's a continuous number, correct? Basically, my house price. It's a continuous number. It could be 50,000, correct? It could be 1,99,999. It's a continuous number, right? It could be anything. By looking at the target variable, the moment I know that it is a continuous number, directly I focus on my regression algorithms. And when I do my regression algorithm, one of the algorithm is linear regression, and I can check. If I check if all the assumptions are true, then I can directly go on apply the linear regression. Correct? Okay. Now, what is the next step after checking my assumptions? What is the next step? Train test split, correct? I need the data to train the model, and I need some data to be kept separately to validate my model. That is, that particular data is the test data, that is a proxy for tomorrow's data. It's an unknown data, correct? What is the splitting criteria? I use 80-20, correct?
Yes, sir.
80% of my data set, I use it to train my model, correct? But the moment I split the data set into 80-20, do I directly go with model training? I need to scale it, right? I need to scale my data set, and then I need to train my model. Okay. And then what will I do with this? I mean, let's say I train my model. What do I do then?
We test
I find out my
RMSE.
RMSC R square. I do my validation. Okay. This is on the training side. Now this 20% of the data set is remaining. What will I do with this first?
We test it.
Can I test it directly? I had scaled my data set here, right?
Yes,
I
sir.
had scaled my data set, no? So I need to scale this model also here. This data set, which was unscaled in nature, I have to scale it here. Okay. And only then I can feed it into the model to get my RMSE and R square. So what next? What do I do next? I compare. I compare it, right, with my train and test.
Yes, sir.
I compare it, and if the variations are justifiable, then I
Accept.
accept the model, yes, or else I try some other model. Is this clear?
Yes, sir.
All forgotten, no?
Yes.
Okay. Let's do one thing. Let's have 10 minutes of break. Let us resume at 12:10. Okay. And then we'll directly start with the Python code.
Okay, sir.
Okay.
Okay, sir.
Is everyone back?
Yes, sir.
Rahul, you back? Rahul, are you back?
Yes, sir.
Okay. Now, this notebook is already in your LMS portal. Hope you have downloaded it. Okay. Now, what we are trying to do is whatever we learned in in today's session as well as in the past sessions, we are going to try it out physically in this particular notebook. Okay. Plus, whatever the structure we just noted down in just about before the break, and we are going to understand how the flow is in the real scenario. Okay, even we'll verify the pseudo codes what we noted down. Okay, what is the point number 1? What is the first step in the project? The first step would be
Problem statement.
problem statement. Yes. So what we are trying to do is we are going to understand the sales part in thousands of units, okay, of a particular product with respect to the budget we are spending, the advertising budget we are spending. So we have the budget we are spending on advertising in television, in radio, and a newspaper. With respect to the budget, we are going to understand how much sales we are getting for the product. Is this clear?
Yes, sir.
Okay. So in general, advertising is more. Advertising gives you more or less sales.
More.
More advertising is more sales, correct? So this is a decent case for linear regression. So a decent case for regression. How can you say it's a regression? How can I say this is a regression problem? Sales is a continuous number, right?
Yes, sir.
Okay. Now, coming to the second step, that is importing my libraries. You guys know about pandas, right? You guys know pandas, Seaborn, Matplotlib. Even you guys know about NumPy and Matplotlib inline. What you guys don't know is a new library called sklearn from sklearn import metrics, correct? Let me just remove this. Okay. Are you guys clear about this block?
Yes, sir.
Okay. Now, coming to the data set. Coming to the data set, when I do my read underscore CSV from a link, I have given index call equal to 0. Any idea why I have given this? Okay. So to understand that, let us verify this. When I see my data set, okay, I have here 1, 2, 3, 4. Okay, I have my index already present in my data set, this particular column. After that, I have my budget in radio, TV, that is 230, then radio, then newspaper, and then my sales. Okay. Is this clear? So that's the reason why I have index column as 0. Let us say I remove this. I get one more column called unnamed column 0, which do not have any column name here, and Python has automatically given the column name as unnamed colon 0 to this particular column. This is nothing but my index, correct? So whenever you come across this issue, when you load the data set, straight away give index column, that is use column 0 for my index. That's what it means. Okay, is this clear?
Yes.
Okay, now coming to the EDA part. Data set, you are clear, right? Sales is nothing but the number of units I sold the product, whereas the radio, television, and newspaper is the amount of money or the revenue what I'm spending on these advertising medias, and what is the sales I'm generating. Basically, I need to develop a regression model. So regression being this target variable being continuous in nature. Okay, so I need to develop a regression model to understand which of the media gives me better sales, or understand a proportion of my investment, my budget, how much percentage of the budget should be invested in my TV or radio to get a particular sales revenue. Okay, now coming to EDA, I see my data sort shape, I see data.info. What do I notice from data.info? What do I notice here? There are no missing values, correct? There are no missing values. And the data type format is already in float. You guys agree with me? Shaina, do you agree with me?
Yes, sir.
Coming to describe. If I look at the target variable, okay, by looking at target variable, can I verify my first assumption of linear regression? What is the first assumption?
The target variables should be
Normally distributed. How do I check it?
by plotting.
Either by plotting or in describe. What do you check in describe? Mean equal to median. My mean is here, which is 14.02. My median is nothing but 50%, which is about 12.9. Okay, the difference is only 1, close to 1, or around 1, correct?
Yes, sir.
Okay, but I need more evidence. I need to plot it, right? So I plot it and I get my target variable here. I have given dspline. If I run it without dspline, I get this particular box. So as the name indicates, dspline, it removes the y-axis. Okay, so this is the distribution of my target variable. I see that it is normally distributed, correct? You guys agree with me? Is this clear?
Yes, sir.
Okay, now we plot a joint plot. Okay, now joint plot is something where you have the distribution of your particular variable. Let's say the newspaper, I have the distribution here, and I have the distribution of sales over here, plus I have a scatter plot between newspaper and sales with the small regression line. Okay, and same goes for the other variables. Okay, so it gives you a histograph and a KD on your x and y axis, plus a scatter plot in the middle. Okay, plus what I do is I also go for a pair plot. I also go for a pair plot. Okay, but it is very difficult for me to understand the correlation in a pair plot, right? So I use data.core or a heat map of data.core. What happens in heat map is basically, if I just plot my heat map with data.core, I get the color representation of how dense the correlation is. And when I give not equal to true, I get the correlation values inside the heat map. Now, is there a correlation? Is there an assumption issue with the correlation? So the independent variables, the radio, newspaper, and sales should not be correlated with each other. Correct? Are they correlated? Especially in this plot, in this area. I would say you just have to look into this particular line, these three lines, and these three columns. Is there a violation of correlation? Shaina? Rahul?
No, sir. All are less than 0.8.
Less than 0.8, correct?
Yeah.
So we are good to proceed. Now, let us verify the other assumption, that is, there should be linear relationship between your dependent and independent variable. So the dependent is sales. I have my sales in my x-axis, and the independent is my target variable, that is not TV is not target variable. TV stands for television. Okay, I have my television, I have my radio, and the newspaper. Okay, what is your feedback on sales versus TV? Is there a linear relationship?
Yes, sir.
Correct. Whereas in
Yes.
radio and sales, what about radio and sales?
Kind of, sir. Not perfect.
Kind of. Okay. What about newspaper and sales?
No, there is
Least, no, least.
Okay. What is the check here? How do I correct this?
no.
We
By
discussed on squaring it or cubing it.
yeah,
But
by
will it help?
shortening the scale over here. I guess.
But will it help here? We
And
can square or cube when there is a polynomial relationship. Correct.
okay.
But whereas here the points are all over the place. No. If I scatter it, I'll just, if I do a square or cube, what happens is my x-axis will get stretched, but the points will just go far. Correct? In very random places. So what is the check we have in linear regression is that the value of beta will automatically get adjusted to a lower number here. Okay. You will realize it when we go to the linear regression part. Okay. And up to this step, is this clear? Is everything clear up to here?
Yes.
Yes, sir.
Okay. Now, coming to the linear regression, you have a lot of notes here. You can go through it, but I'm going to skip it now because we already brushed it like 3-4 classes. Okay. In our theoretical discussion, we discussed on splitting the data set first and then doing the scaling. Okay. But whereas here, we have done the scaling first. So from sklearn.preprocessing, we have standard scaler. You guys know about this standard scaler? You guys remember standard scaler? What does standard scaler do? Basically, it throws out your Z score. How do I find the Z score? This is the formula for Z score. What is X? X is my variable. What is mu?
Mean.
Mean. What is sigma? Standard deviation.
Standard deviation.
So what standard scaler does is
It will normalize.
it will normalize. So what happens in this case? When I do my Z score, in the Z values, we'll have a standard deviation of 1 and mean equal to 0. Correct? It gives you this. This is 0 and this is my value 1. Correct? So how do I do the scaling? From sklearn.preprocessing, import standard scaler. Basically in Excel exercise we did. You guys remember the Excel sheet exercise? How we calculated the Z score? How did it do that? We applied this formula, correct? You guys remember this? While practicing, please open the Excel sheet and understand how did we do the scaling. So that whole exercise, how we did the scaling, is already in this particular library. So from sklearn.preprocessing, import standard scaler. So you guys remember about object and class? You guys know about this?
Learned in Java, sir. This time.
No problem. Just a basic idea would be sufficient.
Yes, sir.
How about Shaina?
Yes, sir.
Okay. So what are classes?
Classes.
A group of
include,
objects.
yeah, group of objects which have methods in it.
Let us keep it very simple. So classes are nothing but my complicated type of variables. Okay. So practically when I say x is equal to 2, okay. So x is my variable and 2 is my
Value.
2 is my value, but this is a value which belongs to class int, correct?
Yes, sir.
So 2 is a number, the type of the number, the type of a variable is int. So when I have a complicated variable. So instead of calling a variable, instead of calling this as a variable, okay, we call it as a class. So, okay. And for this particular number, okay, we call it as a object. Sorry. Anyway, okay. Okay. So this particular number, this particular variable, we call it as an object. So I would say as a summary, the variable of a particular type, that is nothing but my x equal to 2, correct? And the object of a particular class. Okay, these things are one and the same. Are you guys with me?
Yes, sir.
Yes, sir.
So the variable of a particular class, that is x is equal to 2, and the object of a particular, variable of a particular type and the object of a particular class are one and the same. Okay. Now, coming to from sklearn is a module. Under this, I have a library called pre-processing. Inside this pre-processing, I have a class called standard scalar. So once I import this particular class, I'm going to define an object called scalar in this particular class. Okay. Once I define it, I'm going to fit it with my data, and then I transform my data to a scale data. So basically, how is my data looking? My data is looking like this, correct? Now what I do is I am going to scale it. When I give the dot fit, what happens is in the background, the algorithm will just understand what is the factor it should multiply each and every number with. It will only understand the factor. It will not do anything over here. But when I give dot transform, only then it converts my data set into a scale data set, which is stored in data 1. Not defined. Okay. Now, the moment I transform it, it will be in the form of an array. Correct? This is my transform data. This is my scale data. So I need to bring it back to, I can actually work with it, or I can bring it back to my original form, which will look like this. Or maybe I can convert 0, 1, 2, 3 into my columns, which will give back the original shape. Now, if I do data dot describe now, I get my mean as e to the power minus 16, that is 0, and my standard deviation is 1. Are you guys with me?
Yes, sir.
Yes, sir.
Okay. Now, since I have scaled my data initially before I do my linear regression, I have my scale data set. What is the next step? I need to separate X and Y. So my X is nothing but these three variables, correct? I put those values in X, okay, and Y is nothing but, what is the shape of this? I have 3 columns and 200 rows. What about Y? Y is nothing but data dot sales, nothing but my sales column. If I want to see the shape of it, it is having 200 columns and only 200 rows and only 1 column, correct? Is this clear? Any confusion?
No, sir.
No, sir.
Okay, now. So what have we done so far? One minute. What have we done so far? What have we done so far? Imported all the data sets, libraries, correct? You guys with me?
Yes, sir.
After this, what have we done? We did our problem statement. Anyway, we did this one first and this one later. We did our EDA. We checked. Assumptions, correct? Now, we did scaling of data set, correct? We used standard scalar. There's also one more scalar called Winmax scalar. We will use it. I'll explain you in the later stages. Okay. Now for this data set, we used standard scalar. Now, after scaling the data set, we need to do our XY split, where we separate my explanatory variables and target variable. Okay. Once I separate this, I need to do my train test split. Correct? This will be like 80-20. So what happens here is, since I've already separated X and Y, when I do my train test split, I will have X train, okay, Y train, X test, and Y test. Is it clear? Any doubts?
No, sir.
No, sir.
Okay. Once the training is done, okay, normally I can do my scaling here, or I can do my scaling here. Okay, in after the training. Now, if I do my scaling here, I need not take my Y's. I can only scale my X's. That will be underscore S. Here where I will be doing dot fit and a dot transform. Okay. Why do I need dot fit? To understand what is the factor which I need to multiply to this data set or to original data set. Dot fit will only understand what the factor is, and the dot transform will actually do the this function will be the one which will actually do the scaling. This is only the pre-processing step. It will understand what the factor is. Okay. Then for my test data set, do I need to do dot fit again? Shaina, do you think I need to do dot fit again?
No, sir.
Correct. Because you already have the factor. So here you need to do only dot transform. You just have to scale it. If you do dot fit here, you will lose this relationship. This relationship will be lost. Okay. Now, this is the part where you have your data set ready. And once the data set is ready, you apply linear regression. Once again in linear regression, it is very simple. You need to do dot fit and dot, not transform, you need to do predict. Okay. Now, let us go back. So far,
The dot predict, that is for testing, right? After training, we
it
test
is
it.
for training also, for testing also.
Okay.
Okay. Now that we have separated X and Y's, okay, we are going to do the train test split. That is this particular step, 80-20. From sklearn dot model selection, I import train test split. Okay. I need not complicate it by bringing in a function. Okay. These are the simple steps. I use test size equal to 0.2. That means it is a 80-20 split. Okay. After splitting, I have what was the original shape of my what is the original number of rows? How many rows did I have initially? $200, right?
Yes, sir.
Now I have 80-20.
160.
80-20. What is the 20% of 200? 20% of 100 will be 20, right?
Yes, sir.
So multiply by 2 will be 40.
Yeah.
So my test size will have 40 rows, correct? And my train will have the balance 160. Is it clear?
Yes, sir.
Okay. Now, Shaina, is this clear?
Yes, sir.
Okay. Coming to linear regression. Again, from sklearn. Sklearn is nothing but scikit-learn, which is a very powerful library for your data pre-processing and for running machine learning algorithms. Okay. So from sklearn.linear model, import linear regression. That is, import the class, define the object, linear reg equal to linear regression, define the object. You do a dot fit, correct? And do a dot predict down there when you do the evaluation. Okay. I'm going to import the model. I have imported the class, created the object. I given dot fit to my train, X train and Y train. Where did I get this X train and Y train? That is over here, correct? I have imported my train data set into the model. Okay. Once the model is done, what do you expect from the system? So that will be y equal to beta 0, beta 1 x, beta 2 x2, beta 3 x3, correct? So if I have to print the intercept, this is nothing but my beta 0. Print intercept linear reg dot whatever the object you have created. Whatever the object you have created, if you give a dot next to it, you get certain functions. Linear reg, if you give a dot and give a tab, you get certain functions. Okay. One of the function is coefficient. Okay, to view all the betas, and the other function is to view the intercept. That will give you the intercept. This is nothing but your beta 0. So you have your beta 0 and you have your other betas. Clear? Now, if I put these betas into respective columns, if I put these betas into respective columns, you can see here that for newspaper, the beta value is very low. Correct? The beta value is very low here. 0.010 is the beta value. The reason why is there was not much linear relationship here, whereas For TV and sales, we are expecting a higher beta value. And for radio and sales, we might expect a moderate one. Here, I expect a very low beta value. So the linear regression model has automatically adjusted the beta values, correct? You can make the equation something like this. Is this clear?
Yes, sir.
Okay. So far, what have we done? We did the train test split, correct? We did the scaling anyway we did earlier. We applied linear regression up to dot fit, correct? We did our dot fit here. Our model is ready. With that dot fit, we could get our intercept and coefficients. Okay. Now, coming to dot predict. So, for my I already have a Y train data set here, correct? When I did my train test split, okay, when I did my train test split, I already have my train values here, correct? We did not talk about the test values. We already have our train values when we give the dot fit. Now, if I want to do the prediction for my trained model, the trained data set, I will store my with the output, the test, the Y test, I mean the Y predicted for the train, I'll store it here, Y predicted train, and I'll give dot predict of X train, correct? And same goes for my test data set. Okay. Now that I have made the prediction for my train data set, it looks something like this, correct? Any doubts? If I want to see dot shape, this is again 160, okay, and Y train dot shape is also 160. Any doubts?
No, sir.
No, sir.
Now coming to Y test, I have my Y test values here, which is nothing but 40 rows, and I feed my model with this data, which was not at all shown to my model. When I did the model, when I ran my model over here, I never shown my test data set to the model. I generated my intercept and coefficients without showing my test data set. So test data set is something that is proxy for my tomorrow's data. So now I want to understand how well my model is behaving. For that, I feed my test data set, that is basically the X values, into the model, and I do a prediction and store it in Y underscore predict for test. Okay. Now, if I want to view this, here are my predictions for the unknown data. I see dot shape, it is once again 40. Correct? Now, When we apply linear regression, we did dot fit with respect to x underscore train and y underscore train. And we generated what? Doing dot predict. We generated what? Correct? You guys agree with me?
Yes, sir.
Yes.
Now for the test data set, dot predict of x underscore test. I think you don't get train here. Dot predict x train, yes, correct. Only when you give dot fit, which is over here, when you give a dot fit, you feed both x and y values, whereas when you give a dot predict, you only feed the x values. You don't have this here. Okay. Now dot predict will give me, now this is basically proxy for tomorrow. This is my unknown data. This gives me test. Correct? Now, in order to find, once this is done, what do I do is, I need to evaluate my model. Okay. And for model evaluation is nothing but I need my actual minus predicted, it gives me error. So to find this, I can do my model evaluation with respect to train and with respect to test. Correct? And in the end, compare the behavior. Okay. And to train, I have y train and correct. You guys agree with me? Any
Yes,
doubts?
sir.
No, sir.
Test, I have y test and test. Correct. So I should have RMSE and R square here also. R square here also. Basically for train data also I'll have RMSE and R square value. For test data also I'll have RMSE and R square value. Okay. Now, coming to the model evaluation. Up to prediction is clear, right? Shaina, Rahul?
Yes, sir.
Yes, sir.
Okay. Now, you did not break your head for mean absolute error or mean squared error. We will cover it in model evaluation. We can focus on root mean square error. We already have brushed up with the formula. So, in Python, we have mean squared error. Okay. We get mean squared error. Okay. That is nothing but whatever the elements you have inside the square bracket, inside this square root. That is your error. You square the error, you take the mean. Up to here, you already have a particular function. But in order to find the RMSE value, you need to have square root of it. That is something you need to use np dot square root to get the mean squared error for your train value and your predicted train value plus your test value and your predicted test value. So I'll save it as RMSE train, RMSE test. Okay. And then when I print it, I get for training, I get it as 0.33 and for testing, I get it as 0.271. Is this good or bad? RMSE should be as low as possible, right?
Yes, sir.
Yes, sir.
So it is good.
It is good, no? Is this clear?
Yes, sir. Yeah.
Okay. Now, coming to R square. You need not go through this formula because this is more into what I explained in the class. Basically, how we've calculated the total variance and unexplained variance, correct? So all this is considered over here. You do not break your head for that. So in Python, we have a built-in function in the same module, sklearn.metrics library. We have a built-in function called R square, R2 score. Okay. I find it for my train data set and find it for the test data set and I print it. I get the R square error as about 89.5% for my training data, and for testing data, I get it as 89.3%. Is this good?
Yes, sir.
It should be between 0
Yes.
and 1, right? It's a pretty good model, right? You have about 89% accuracy, correct? Okay, any doubts?
No, sir.
No, sir.
So which was more easier, theoretical or practical?
Practical, sir.
In theory, we did a lot of paperwork and we did a lot of exercise in Excel also to do a prediction, to do an error. Whereas it's just a single 2-3 lines of code, you can get to finish everything, correct? Especially the regression part, you finish it in like 3-4 lines. Correct?
Yes.
But ultimately, you need to practice a lot. In order to understand this, in order to get a grip of the subject, you need to practice. Okay. Any doubts in any section?
No, sir.
Okay. Now, coming to the last part on the application. We have already taken all these examples in our initial study only on the application to find the house price. What is the age based on the input variables, correct? To find the car price, to find the insurance premium charges. Okay. These are few of the application of your linear regression. Even there is a app called there is an application through which you can sell your used mobiles. You guys know about it? There's an application, not able to remember the name. Let me just check it. Which helps you to sell your used phones Okay. Okay, the app called Cashify. Okay, there's an app called Cashify. Basically, what it does is it once you need to install the app in the particular phone which you want to sell, and this particular app learns all the algorithms to take it takes all the input variables, like if your charger port is working, if your power button is working, is there any issue with the display, or is there a is the speaker very clear, are you able to call people. So it is going to take all the inputs, and based on how you get the inputs, okay, it will give a price of your mobile, and upon submitting your request, agent will come and pick up the mobile and transfer the amount. Okay, so that basically runs on this particular regression model. Okay. Any doubts?
No,
Shaina, any doubts?
No, sir.
Okay. In the next class, when you come, let us work on one of the classification model called logistic regression. Okay. Basically, this model will help you classify things like apple, banana, grapes, or something like whether to issue the credit card, whether to issue a credit card to a person based on different factors, such like income, do they have any loan, what is the present income, and all that. Okay. In case you have any doubts, you can stay, or else you can drop off.
no doubt, sir.
Okay.
Thank you, sir.
Thank you, sir.
Thank you.